Welcome friends, Igor is here, and in this video we will discover an interesting property of linearly dependent sets of vectors. In this lesson we will prove that linearly dependent vectors in fact depend on each other. Let's get started. Our main result is this. A set of vectors is linearly dependent if and only if one of the vectors in this set can be expressed as a linear combination of the other vectors. This is an if and only if statement, and this means there are two separate implications for us to prove. First, if a set of vectors is linearly dependent, then at least one of the vectors in the set can be expressed as a linear combination of the other vectors in the set, and then conversely, if one of the vectors in the set can be expressed as a linear combination of the other vectors, then this set of vectors is linearly dependent. Let's start by assuming that the given set of vectors is linearly dependent. By the definition of a linearly dependent set, this means that there exists at least one non-trivial relation of linear dependence on this set. And a non-trivial relation of linear dependence means that not all scalars are equal to zero. There must be at least one non-zero scalar. We don't know which one it is, so let's say it is a scalar alpha t. Then I'm going to take the given relation of linear dependence and add the negative of vector alpha t ut to both sides of this equation. On the left-hand side, we are going to use the commutative property of vector addition to take this newly added vector and move it right next to the vector alpha t ut. On the right-hand side, we are going to use the property of the zero vector, so that it simply disappears from this equation. Notice that on the left-hand side, we have vector alpha t ut plus the negative of this same vector. By the property of the negative vector, we know that these two vectors add up to the zero vector, and zero vectors simply disappear from the expressions because they do not change other vectors when you add the zero vector. Therefore, this equation simplifies as follows. So far, I have not yet used the assumption that alpha t is a non-zero scalar. Now is the time to make use of this assumption. Because alpha t is a non-zero number, it does have multiplicative inverse, which is 1 over alpha t. So what we're going to do is we're going to multiply both sides of this equation by the scalar negative 1 over alpha t. This number exists because alpha t is a non-zero scalar. Now we simplify this equation using properties of the vector operations. On the left-hand side, we distribute the scalar multiplication over vector addition, and then on both left-hand side and right-hand side, we use the associative property of scalar multiplication. In particular, the right-hand side simplifies to the vector ut. But now you see that the vector ut is equal to the linear combination of the other vectors in the set R, and this is what we were trying to prove in this implication. In the opposite direction, we are going to assume that one of the vectors is a linear combination of the other vectors in the set. So let's assume that it is the vector ut that is expressible as a linear combination of the remaining vectors. So what we do is we write this linear combination expression. So we know there exist some scalars, let's call them betas, so that the vector ut is equal to the linear combination of the other vectors in the S in the set R with the given scalars beta. Let's add the vector negative 1 times ut to both sides of this vector equation. On the left-hand side, I am using the property of vectors that the vector is equal to its scalar multiple by the scalar 1, and on the right-hand side, I'm going to use the commutative property of vector addition to move the newly added vector in its proper, in a sense, position in the linear combination of all the vectors from the set R. Next, on the left-hand side, we are going to use the distributive property of vector operations. But now you see that the scalar on the left-hand side becomes 0. And of course, given our explicit definition of the operation of scalar multiplication, you understand that if you multiply any vector by 0 scalar, what you'll get is the 0 vector. But what we have now is a linear combination of the vectors in the set R that is equal to the 0 vector. In other words, this is a relation of linear dependence on the vectors from the set R. I claim this relation of linear dependence is non-trivial. To see that this is a non-trivial relation, all we need is to ensure that we have at least one non-zero scalar. Do you see which scalar is non-zero? It is the scalar beta t, because it is equal to -1. For sure, -1 is not equal to 0. So this means the vectors in the set R are linearly dependent, because we have found at least one non-trivial relation of linear dependence. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discuss how to describe spans using as few vectors as possible. I will see you later.